Hello everyone, good afternoon. I think we can start now. Marcus is here since Sunday afternoon, so I don't think that I have to introduce him the detail, but briefly speaking, I will just speak with Marcus obtained his PhD from the University of Bonn in Germany in 1997. And for his PhD, he did the research work at Max Planck Institute for Astronomy. After his PhD, he went to the United States, where he was a postdoctoral fellow at Rice University, Houston, Texas, from 1997 to 2002, which also included a tenure of Chandra postdoctoral fellowship from 1999 to 2002. That Chandra postdoctoral fellowship later became Einstein postdoctoral fellowship, and now it comes under the NASA Howard Fellowship program. Since in 2002, he became assistant professor at Ohio University, Athens, and associate professor in 2007 and full professor in 2012. In 2013, he moved to South Africa to take up the position of SARChI Chair of Astrophysics and Space Physics at Northwest University, Potchefstroom, South Africa. His area of expertise is theoretical high energy astrophysics with special emphasis on extragalactic sources such as active galactic nuclei and gamma ray bursts. He is the chair of the South African Gamma Ray Astronomy Program, coordinating the high energy astrophysics research activity and funding needs of about 100 members at 6 institutions in South Africa and Namibia. It is our pleasure to have Professor Markus Boettcher with us. So, Professor Boettcher, welcome. And I request you to deliver the colloquium titled Multi-wavelength Polarization as a Probe of Astrophysical Relativistic Jets.
Thank you very much for the introduction. It really is a pleasure being here. In about 3 days. Yes, so before I delve into the actual topic of my talk, where I come from, I'm not pretty sure it knows where Potchefstroom is, but just in case there's anybody who doesn't. So, I'm from South Africa, and Potchefstroom, we're about north central South Africa, about 20 kilometers of Johannesburg. What many of you may know about South Africa, very famous Kruger National Park, that's in the northeast corner of the country, right here. Very famous for tourists. The famous thing that I like very much is our wine region around Stellenbosch, the Cape. So if you want to enjoy reading of wine, either go to surroundings or come to Potchefstroom, where I actually eat something this wine tasting seven. Anyway, so why welcome to South Africa from a little bit more about from desert there, so it's been civic desert, savannah, landscape, like that. Scale was national park nearest national park to us. That's all pictures of the life path. It's 2 hours drive from the nearest national park. So then, of course, the question why come to South Africa? We have reasons why. The reason why was there's a lot of astronomy happening on South Africa. So what it's doing, we are sure referring lots to the developments in astronomy. There's mirror cuts, so the radiating ray in 64 and 16 meter dishes that will actually grow into the spectropolarimetry ray. We run all of South Africa stations all the way out to its clarity. We also have the world's largest Stereoscopic telescope in India. So we can install this. And we have the largest single optical telescope in the southern hemisphere, the Southern African Large Telescope. In South Africa, it's about 412 meters. Active in high energy astrophysics and gamma astronomy, institutions primarily, plus the University of Potchefstroom, the two universities in Johannesburg, Ritz University and the University of Johannesburg, Free State in Bloemfontein, It's the sort of Western Territory in Cape Town, and the English of India. The South African member astronomy by engineering since 2013. Six institutions. So now up to the galactic nuclei, and in particular blazars. So relativistics. As the name said, galactic nuclei, they're the central regions of their galaxies. Very peculiar properties, they're extremely bright. So they're nuclear regions that outshine the entire billions of stars of the entire galaxy by factors of hundreds of thousands or millions even. Clearly, this cannot be powered by just a lot of stars there, cannot be simply one. We know them to be variable, extreme cases, 100 minutes time scale, while at the same time outshining an entire galaxy by factors of thousands. We know that they are high energy emitters, particularly the most numerous class of sources that we see gamma rays with gamma ray astronomy satellites outside of our Milky Way. Optical spectra show emission lines, as being ionized, energetic central source. Their emission from radio to optical, and since a few years we also know X-rays, which is polarized, its figures into this. Some have these mysterious relativistic outflows that they will focus on very much, called jets, streaming out almost the speed of light from the central regions. All of this is very strong evidence that this is powered by mass accretion onto a very massive black hole. We know now that essentially all galaxies that we know have a massive black hole of millions or even billions of times their mass portion. In the case of our own Milky Way, we know there is a big black hole of about 4 million solar masses. But in this case, there's essentially no matter around to accrete it on. In the case of active galaxies, the case is different. We have a supermassive black hole. Many of these H.E.N. active galactic nuclei have abundance of solar mass black holes in there. And there is a lot of gas around, it accumulates, forms conservation, that accretes onto this black hole, it heats up during viscosity, emits X-rays. And in some cases, about 10% of cases of these active galaxies, this goes along not only with the fusion of gas onto the black hole, but ejection of streams of gas with jets along the symmetry axis. We know that these are streaming out with essentially the speed of light. So the picture we have from the components in the galaxy, let me show us here so that I can see it. So we know it's powered by central black hole in the middle. There's gas right around it, treated in the accretion disk that heats up to millions of degrees, thereby emitting ultraviolet rays. This is fed on larger scales by some colder, dusty material called the dusty torus that sometimes obscures our view when we see these things from the side. Then there's gas above and below the disk that essentially surrounds the central black hole. And the closer it is to the black hole, the faster it has to go. It moves fast. It's ionized by central accretion disk. If it moves fast, these emission lines that result are broadened out by debroadening. So close black hole, we have gas clouds that broaden emission lines further away. These clouds move more slowly, so we see narrower emissions. Now, what kind of H.E.N. we see depends on how we look at this H.E.N. If we look from a direction where we have a clear view of that central region, we see both the narrow and broad emission lines. So this type 1 H.E.N. And if we look from the sides that this dust storm obscures our view to the center, call it type 2 H.E.N., where we only see narrow lines from the clouds that are further out. And if you're familiar with IUCAA, and you know the space right out here that is supposed to represent such an H.E.N. So the two pairs between the accretion disk, black holes in the middle, it's still, I see courageous people walking straight through the black hole, and so they still manage to make it through. The jets are the axis perpendicular to it. All right, so now if we focus on these text-dominated AGNs, so these outflows with almost the speed of light, and what we see depends very much on the orientation which we see. We happen to see it right from the side like this. We don't actually see much of the jets in a region here because they're moving with essentially the speed of light directly perpendicular to us. So we'll discuss in the more detail in a few minutes. Means the radiation is actually boosted away from us so that we can't really see it. But we only see where it eventually dissipates and electrons accelerate and we see synchronous radiation. So we see this as radio galaxies, radio emission from the termination of these jets. And in fact, these jets are in many cases much larger than the entire galaxy actually. So the galaxy is really just about the extent of that little white block we see here. The jets are often much larger than the ones to hundreds of kiloparsecs. Now we happen to see in a few percent of these cases, we happen to look right down the barrel of the jet, and just a few degrees or so. We see relativistic effects of Doppler boosting and relativistic aberration. We see essentially only this one jet turns the point towards us because, well, there is another jet going the other way. Its emission is boosted away from us, so it's much further toward us. So that's why we don't see what it looks like with only one jet. We just don't see the. So now, Blazars. For this class of AGN, I see the jets right down to the middle of the tube. Consists of the objects and camera right. Blazars distinguish by whether they have these broad emission lines that we see when we look down from the central region, or they don't. If they don't, we call them objects. Probably not so much that they won't have this accretion flow, and that we just look at them from the side. So I think they're intrinsically fainter so that we don't see those lines. We see the most rapidly growing of emission that we see. Then we see in extreme cases variability down the minutes. Now, the gamma ray sources that we see, for example, with the Fermi Gamma Ray Space Telescope and with ground-based gigantic telescopes like H.E.S. that I mentioned before, my overview of astronomy and Southern Africa. We see a funny effect of individual knots of blobs along these jets. We can follow with high-resolution radio observations over many years. They appear to be moving faster than the speed of light, called superluminal motion. I'll discuss that a bit more in a few minutes. To show high polarization. More details to that variability. You see here light curves over several months here with several wavelengths. We see the top panel that is Fermi Gamma Ray Space Telescope, gamma ray light curves, index and gamma rays, and this X-ray light curve. The third panel, optical, polarization here, polarization degree, polarization angle, infrared and radio light curves. You see, first of all, it's not that the whole spectrum just goes up and down, everything does the same. We really sometimes have one thing, another band doing something totally different. Sometimes they do the same, sometimes they don't. This complicates the matter. We see degrees of polarization of typically less than about 30%. Much more about polarization, that will be the focus of my talk later on. But it tells us that we don't have perfectly ordered linear fields. And we see that both the degree of polarization and polarization angle are often relatively variable. Particularly, there's one event here. We see polarization degree dropping very rapidly in a few days of recovery. This polarization angle is making a whole swing of more than 180 degrees. Going along, flaring and gammas, which is not really full abstract. There's a lot of videos comparing. So you can see the main message here being variability can be very important and most importantly, predictable. So if we plot their spectrum and spectral energy distribution all the way from radio waves to infrared optical X-rays, gamma rays, that is very strongly dominant along thermal emission. So not like in this normal galaxy where you just see a superposition of this lot of stars. It's mostly infrared optical and ultraviolet. Here we see emission really across the entire electromagnetic spectrum, where we pretty well understand now this low edge component from radio to optical, in some cases UV and X-rays, and synchrotron radiation from relativistic electrons. The high energy component from the X-rays to gamma rays, in some cases up to very high energy gamma rays that we can see with ground-based telescopes. That can have either electronic or hadronic. For the further discussion, it's useful to mention a bit about the classification. These blazars are classified essentially by location of low frequency below a synchrotron. If that is below the optical range, talking about low synchrotron peak blazars, so when the synchrotron peak is below 15 Hertz, those are flat spectrum radio quasars. With all flat spectrum radio quasars that we know belong to this low synchrotron peak class, but there's also some BNL objects with low synchrotron peaks. On the extreme other end, we have sources for the synchrotron spectrum peaks in the stress, and the gamma ray spectrum can actually peak beyond the Fermi gamma ray range, the 100 GeV energy range. This is called high synchrotron peaked blazars that essentially are objects. So along with this shift of the synchrotron peak, often also goes a shift of the relative output in synchrotron against high energy. So low energy peak blazars typically are dominated by the thermal emission, whereas the high synchrotron peak blazars are often dominated by the synchrotron emission. And then they're sort of in between those intermediate synchrotron peak blazars. So this sequence is often referred to as the blazar sequence. Now a little bit more about synchrotron emission. This is what I was talking about. So in the top and middle, you see time ticking away. So it's a real observation sequence of images from my favorite quasar called 3C279. So the coordinates now on the top left. So over time, you can see one component of this jet gradually moving out. It's slow here, but the thing is very, very, very far away. It's a direction of more than 0.5. So converts that velocity with which this component moves out into a spatial velocity, gives you many times the speed of light. We'll show what the actual number here is. It's something of the order 10 to 15. It means 10 to 15 times the speed of light. So I think everybody here, when they organize these physicists, we first think in spatial relativity. So is that all wrong now? Luckily, what's actually happening is, I have to apologize to other third students. You've seen 90% of the slides that I'm showing you before. So sorry about that. And in words, you've heard almost all the jokes before. But I'm still going to remember. So what's happening here? That's the component of the jet that emits multi-wavelength radiation is moving around the jet almost the speed of light. What it means is that when the light radio waves or that is emitted, it's only a tiny head of that field. It's not like this from here reaches us now, then from here reaches us whenever it's emitted. Well, the information only travels with the speed of light. The component catches up, almost catches up with the light that it's just emitted. So by the time we receive it in a much, much shorter succession. And that gives us the impression that this happens in much shorter time scales than it actually is. So this translates into a limit on the Lorentz factor with which the moves along here, or at least a multiplicity of the speed of light with which we see this moving. So we see these moving with something typical maximum of about 40 times speed of light. It means that these must be moving with extremely relativistic velocities of Lorentz spectrums to typical values of opticals. So what does that do to radiation? So let's say this little red blob there, its own frame, we move along with it, it's moving as it is radiating isotropically in all directions. There is some intrinsic frequency, U prime, intensity, and time intervals on which stuff is varying. This relativistic motion causes the radiation to first bunched up in the forward direction into a small cone of 1 over gamma, 1 over the Bott Lorentz factor, causes the intensity to be enhanced by 3 orders of magnitude or 3 factors of this Doppler factor, which is of the order 10. Frequencies all blue shifted to higher frequencies, higher energies, by a function of this Doppler factor. And then the fluxes also shifted up by a factor of thousands. And time intervals, variability time intervals, also shortened by that factor. So we see these things varying, they're actually 10, 20, 30 times shorter than they actually do intrinsic. That explains why we see so rapid variability in source is extremely. And typically we represent things in mu space as the SEDs that I've shown before, the spectral energy distributions, means the total polarimetric outputs that we infer is actually a factor, Doppler factor to the 4th power higher. So if that's of the order of 10, then we get the impression that they're actually 10,000 times brighter than they really are. So if we convert the flux that we see into a luminosity, we're tricked into believing that they're actually like 10,000, 100,000, 100,000 times brighter. So now, another experiment. I apologize to the foreigners. I have written stroke before. So we know this is a very complicated structure here, of course, as this jet extended, moving with all the speed of light, interacting. But surprisingly, we see in the picture of the spherical cow works surprisingly well for many aspects. So the spherical cow, of course, we know that for a cow as well. For a complicated system like this, it's actually quite simple. We can straight further to before. It's when first and Joe is holding to me, so I thought this is particularly appropriate in India. Sorry about that. So now we have our shaped emission region. Some mechanism will manage to assimilate particles to relativistic energies, typically in some non-thermal distribution. It will be modified by other effects like cooling or escape. And then we have a radiating electron distribution that will make our synchrotron component. And if it's only the electrons that dominate the radiating output, then it's these same electrons that upscatter low frequency radiation, quantum scattering, like synchrotron self-content scattering that same synchrotron radiation up, or external radiation fields from the accretion phase, dust storers from the broadline region. There's plenty of external radiation fields that can be scattered that can also contribute to this plane change. But it's all the same electrons that make all the radiation. Now, if in addition to electrons, we also manage to accelerate protons to extremely high energies, we still have the same picture for this electron synchrotron radiation, but the high energy emission can in fact be dominated by radiated output from protons. It can radiate synchrotron as well. Synchrotron works for any charged particle, electrons with photons. All electrons need to be accelerated to much, much higher energies. But the assumption in these models is that these jets manage to do so. And in addition, these protons can then also interact with low energy radiation, either from the synchrotron radiation or these other external radiation fields, which use ions. Neutral pions decay to 2 gamma rays, charged pions decay to muons, the positrons, and imports produce neutrinos. And we will not have time to talk about neutrinos in this talk, but this is one of the more recent developments it seems that Blazars are actually source of some of the astrophysical neutrinos that the IceCube detector on the South Pole has detected. There is clear indication that this must take place to at least some extent in Blazars. So now that was the basic introduction to Blazars. So some of the big questions that we have been studying for decades. It's no progress. In fact, these questions have stood for at least 40 or 50 years. We don't really know what powers the jet. Is it powered by the magnetosphere, a black hole? Is it powered by the accretion gas? Just in this workshop, it's probably a combination of both. And what is the physics of actually launching these jets? How do they manage to stay collimated, accelerated for these Lorentz factors of 10, 20, 30, 40? What's the role of magnetic fields in the processes? What they're made of, electrons, protons, or electrons, positrons. And that then relates also to whether the high energy emission is produced by electrons or protons. What accelerates the particles individually to these extreme energies? If you see radiation up to electron volt or even tera-electron volt, must have particles that have at least that energy. So somehow nature needs to manage to accelerate particles to these extreme energies. And then find where it's really. We don't quite know if this happens very close to the black hole, somewhere, maybe parsec. Some evidence that some of this happens actually 10, 100 parsecs out. So we still don't know where all this happens. So first thing one could try, for example, distinguishing electronic versus hadronic models is just try to fit the spectral energy distributions of it. The problem you see here is red is the electronic model, green is the hadronic model. You can see they both pretty much do an equally good job. So that's just we need more. And there's at least 3 different ways you look into that. One is the smoking gun signature of hadronic processes would be neutrinos, but they're very difficult to detect, and they would be a completely different talk. I just gave a lecture about this morning. Variability patterns between these models are actually a bit different. If one sees the variability in the high energy component being decoupled from the low energy ones, which might be a good indication that it's actually different particle populations, like protons versus electrons that make those. Even though we don't really have a clear-cut signature like that in any observations. And finally, I'll show that polarization can be a distinguishing factor. It's the main topic of this. So, polarization. Polarization means that the electromagnetic waves, light, radio waves, X-rays, have a preferential orientation of the oscillations of their reactants. Very well understood is the case of synchrotron radiation. Synchrotron radiation by law distribution of electrons with some index P. Very well understood. If you mix with polarization in a perfectly ordered magnetic field, of this value here equals 1, what equals third. That's the same as alpha plus 1 alpha plus 5 where alpha is the index of the radiation spectrum that emerges from this. That's P minus 1. So if we had a perfectly ordered magnetic field, we would see polarization degrees of around 70%. So for typical indices, but it's much higher than what we actually see. Realistically, you don't expect any astrophysical scenario where you have a perfectly ordered magnetic field in a region where you radiate. But so that's the fact that also content scattering is polarization dependent, which promise that is beneath the last formula that we have found here, and last formula that we have on top. If one writes down the expression for the cross section for content scattering, risk frames, we call electron there. Photon coming in with energy epsilon, where that's normalized energy with respect to past energy, and scattered into normalized energy. Now, the Thomson regime, that's again the 6th ordering regime, where the energy of the photon in the electron stream is much less than the electron mass energy. Then the photon essentially bounces off with the same energy, epsilon equal because we have the V plus 3 plus 2. This cancels out. And we only have this dot product of the electric field vectors for Laplace calculated. Now, assuming you wanted to scatter a photon that comes in with a vertical direction, scatter it in the vertical direction, and the new polarization director would have to be in the horizontal, perpendicular to the propagation direction. It's also perpendicular to the cylinder. So that dot product is 0, that doesn't happen. So what is happening differentially, as we can see directly from this expression for the cross-section, as you scatter differently, perpendicular to the incoming polarization. You tend to preserve the polarization that maximizes the dot. That means if you have a system with electrons, you have essentially a directed beam of radiation coming in. This goes from the front, from the top, and you scatter to the right. Then you're filtering out the degree of polarization usually perpendicular to the screen. Because radiation that comes in the polarization in the plane of the screen will not carry that direction. So this direction-dependent content scattering can induce polarization. This will actually be figured out if we're scattering by relativistic electrons, because then the electrons will see a radiation field strongly affected by relativistic aberration, coming essentially all from the forward direction. So whatever angular distribution the radiation might have had is smeared out in front. We have unpolarized target photons for relativistic content scattering. Polarization. If we have polarized target photons, I can place a synchrotron includes scattering and transfer of content, then the original synchrotron polarization will be reduced by about the polarization in SSC. In the ideal case, that we have ordered in single zones, one of my former PhD students, Hao-Jing Zhang, and figured out that there are much more complicated effects coming in if you have multiple zones. For synchrotron, if you have a combination of synchrotron emission from different cells with random field orientation, you would expect this synchrotron polarization to be reduced by a factor of square root of 1. And it's the number of cells. In the case of SFC, this reduction is much more. So Hao-Jing has figured out that that's something of the order into the power of 5/6. So if you have a complicated system with tens or hundreds of different cells, random magnetic field orientations, that will essentially reduce the degree of synchrotron self-content polarization to undetected levels. Realistically, we don't expect to see polarization in high energies if this is a C polarization. Now, about CN polarization, I think there is no one can detect polarization from astrophysical sources, so with X-ray satellite instruments. One, exploit the polarization dependent of content scattering that we've just discussed. So you have the beam of X-rays coming in, connected by your detector setup. We have a medium that scatters these X-rays once. Then we expect polarized X-ray beam to be scattered perpendicular in the direction of polarization. In other ways, source comes the magnetic field to this, it's synchrotron, polarization direction that way. You would expect the counts in the detector to be essentially asymmetric with an axis perpendicular to the direction of polarization. This is actually being exploited by the Indian AstroSat CCT detector. Alternatively, photoelectric absorption is polarization dependent. So X-rays come in, kick out an electron from atom. The electrons then kick out primarily along the direction of the plane of polarizations. Here we get out this way. So here the situation is then exactly the opposite. The polarization direction is this way. You'd expect the counts to be as asymmetric in the direction of the. This is being exploited by both several dedicated X-ray polarimeter. So far, it's the Imaging X-Ray Polarimetry Explorer, IXPE, that was successfully launched in December 2021. Observes polarization into the H.E.S.S X-ray range. Much more about expectations, what one expects to see in polarization across the electromagnetic spectrums. Now here we have the X-ray range. There will be future mission COSI, content spectrometer and imager that is expected to have polarimetry capabilities in the hardness for the subprimary regime, not maybe energies, which we will speak. But show everything here, including the optical range, where of course we have optical polarimetry and spectropolarimetry from observations. So we can start out with thermal components, infrared plus here. There's the accretion disk that radiates in optical UV. That is, of course, unpolarized. It's just thermal radiation. If the high energy emission is produced by electrons, then, well, in both cases, we have electron synchrotron making up the low frequency component. For a very optimistic, pretty well ordered magnetic field, would have maybe a pretty high optical polarization degree for the synchrotron component. But if there's a significant contribution from that unpolarized component, then that will show that here, then it will reduce the polarization because we can only measure the total polarization of everything we get. There's a significantly polarized contribution, then the polarization will actually be much lower than that of synchrotron alone. And then in the high energy component, say there's a synchrotron self-counting component, can be moderately polarized. Again, this would be only for a single zone setup, multiple zones, and more turbulent magnetic field. It will be much, much lower. Realistically, as we said, it would actually be at undetectable levels. And its external content, this component, will be unpolarized again. If the high energy emission is made by radiation processing, then it's either proton synchrotron or it's from cascades induced by very high energy gamma rays that are made by restricted products. That's all synchrotron radiation, so everything that comes out would be synchrotron. So I expect a degree of polarization here that's actually of the same level of what you might expect from the electron synchrotron. There's a high degree of polarization in the X-rays, and the sources where we see the high energy component of the X-rays would be a strong indication that we're dealing with hadronic processes. It's been, for the first time, I think specifically calculated again by Jing Zhang, a former PhD student. It's the first result of his PhD work, who has used SED fits that we published earlier. This is the spectropolarimetry distribution from ultraviolet all the way to gamma. This is about the IXPE range. This is actually higher energy range. I think that also in the lecture, that was at the time when there was still a hope to detect soft gamma ray polarization from very high. It's captured here being what I just said as the hadronic models in green, getting significant X-ray polarization, much lower darkness. And then in intermediate synchrotron peak blazars, there may be a chance to see some of the synchrotron emission actually peeking into the X-rays. You can see much higher X-ray polarization. Otherwise, the situation is the same in the low synchrotron peak blazars. Real observations now. BLSRT is one of these low synchrotron peak blazars, one of the first that have been observed in the results being published. And here we see systematically no significant polarization. Most importantly, the X-ray polarization much, much lower than the optical polarization. That is very strong argument against this being hadronic, emission, which would be polarized by the single length. It has been done for several other LSB blazars with some spectrum radio quasars, intermediate synchrotron blazar. In all of these cases, we see systematically low detectable X-ray polarization, in particular limits that are much below the optical polarization. So this is very systematic support that's most likely not from the dominated high energy emission, but it's most likely SSC. That's polarization levels that you just detect. Some other aspects of polarization in these low synchrotron blazars. Again, this is CT here. This is now from infrared through optical space gamma rays. For example, so if we see synchrotron dominated low energy emission, there is a component from the accretion is polarized. You can see that here in blue, the total polarization, for example, decrease towards frequencies. The synchrotron, the accretion disk component comes in and dilutes the polarization. Even if one cannot really see that directly in the spectrum, and can't really distinguish that, polarization would allow us to distinguish it. Because from the underlying synchrotron spectrum, we can easily predict what the synchrotron polarization would be. If the observed polarization at high frequencies falls short, that is an indication that there is another contribution coming in. So that we have exploited using thought. Introduced the Southern African Large Telescope, the biggest single optical telescope in the Southern Hemisphere, where here on the right we show a function of frequency and degree of polarization. Fitted to a model where we have the ECD composed of synchrotron and an accretion disk. Blue points are archival, not at the same time as these optical points, at the same time as salt. So we do not need to fit these blue points because that represents a different state at a different time. And here we can systematically disentangle between synchrotron and accretion disk. You see the synchrotron here, accretion disk added to that. See the synchrotron polarization. See how systematically the accretion disk reduces the degree of polarization to the observed limits. And with that, can actually pin down the accretion disk spectrum and thereby indirectly measure the mass. So this is work with PhD students who graduated quite recently. Another example of this is quite famous flat spectrum radio quasar, Parks 1510-09. Those that is regularly monitored by H.E.S.S, one of the very few flat spectrum radio quasars that could be detected in very large cameras. We see very funny variety. Normally, when one looks for interesting variability, one looks for some outburst, so something exciting happens. Here, exactly the opposite happens. We have a very active state in the beginning here up until mid-2021. Then in 2021, suddenly, so this is the Fermi gamma light curve, at the top is H.E.S.S light curve, because H.E.S.S cannot observe all the time, because it needs dark skies and moonless skies. But high state here, very high state, yes, optical, also very active. And then suddenly there's one day. It's very low levels, whereas the X-rays, the very high gamma rays, actually stay where they are. So very weird behavior that has not been seen before, which seems to indicate quite clearly that X-rays and very high energy gamma rays are made by some region and the optical and Fermi gamma rays and essentially just go. So we've modeled that. So luckily this was also one of the first times that we have accompanied our high energy ray monitoring by H.E.S.S with spectropolarimetry results. And there we see the similar effect. Optical, most likely due to synchrotron. Afterwards, when salt was observed again, the polarization essentially vanished. So whatever is there from this jet component that made the gamma rays, the optical polarization, all seems to have just appeared. So we model this again, spectral models with two different components. So one far away component that is not affected by absorption effects, and it's essentially not variable. That's the blue component here, and it just stays there, presents the low state after this disappearing event, and the high state before, dominated by second components that apparently just disappear. It was responsible for the optical emission. You see the blue low state. The optical emission is consistent with only being dominated by the unpolarized emission disk. So it's again where the spectropolarimetry, before the transition, you see synchrotron, which is diluting the polarization systematically towards lower wavelengths, higher frequencies. It's plotted as wavelength. And afterwards, we see essentially low polarization. So something must have kind of switched up that one jet components that made the optical and gamma rays and the polarization. So maybe this was due to the jet maybe swinging onto the line of sight or some other effect. We don't know what it is. It's something that has been seen before. So that we've published with the H.E.S collaboration for years. Now, for high synchrotron peak lasers, we have totally different behavior, because in high synchrotron peak lasers, the X-rays are actually part of the synchrotron component. And there was predictive work, so before the launch of IXPE, a group of Fabrizio and Italy, that, well, if whatever accelerates the particle is some turbulent process like magnetic recollection, you don't expect any globally ordered magnetic fields, expect very low degrees of polarization. Whereas if it's some localized acceleration mechanism, shock acceleration, you would expect at the shock the highest energy particles being accelerated, the magnetic fields being strongly compressed, highly ordered, the highest energy electrons radiating right there near the shock, where the magnetic fields highly ordered, the high degree of polarization. Whereas the longer time the electrons have to cool, the more they diffuse out to larger regions, where the jet again becomes more turbulent, the field becomes more disordered. You see much more disordered magnetic fields globally on average. So at lower frequencies, radiated by lower energy electrons, you expect much lower degree of polarization. This was a prediction before the launch of IXPE. A similar thing was actually seen by Prof, not looking at one source, but looking at the whole sample of wavelengths and monitoring optical polarization. Where, so in the case of the synchrotron peak lasers that we've just discussed, near the shock, the highest energy electrons produce about the peak of the synchrotron radiation X-rays. Then much lower frequencies, optical, we see the much more disordered, larger scale jet, low degree of polarization. Here we plot as a function of synchrotron frequency for different lasers, the average degree of polarization. So the synchrotron peak frequency for different lasers versus degree of polarization in optical. Now, in the opposite case, if we are looking at low synchrotron peak lasers, the synchrotron peak is in the optical. So you will see the optical electrons near the shock at high ordering of magnetic fields. And systematically, we see the higher degree of polarization. Obviously, there's a huge scatter. This seems to be variable in all aspects. But systematically, we do not see high synchrotron peak lasers with very high degrees of polarization. Overall, on average, the trend is synchrotron polarization going down the further you go away from the synchrotron peak with optical frequencies. All right. High synchrotron peak lasers have been observed with IXPE, quite a number of them. And so this is one of the typical high synchrotron peak lasers from CAR 501, one of the best observed. here we see very significant degree of polarization. So I've done to introduce Stokes parameters in this topic here. This is Stokes Q and U parameters. Any deviation from zeros, the distance from zero, essentially gives you a measure of the degree of polarization. We see that these points here for the different observations are also systematically away from zero. So there's a systematic detection of polarization. Most importantly, the polarization is systematically larger than the one in optical and tau fields. So the left panel here shows in one frequency degree of polarization for different observations. You see that the X-ray polarization here is systematically much higher than optical and Fourier. You see this also here. The light view of polarizations, the IXPE polarization is systematically high. Similar thing have actually been seen for all other temperature blazars that have been observed. But this would be too easy. Blazars don't really play along that easily. What is plotted here is now in this curve. Lower panel of the degree of polarization. Red and blue points here are the IXPE X-ray polarization measurements. Degree of polarization, again, X-rays, consistent with being essentially the same throughout this entire range. So this is a range, I think, about 2 weeks or so. So there's no degree of polarization change. But in the top panel, you see the polarization angle, so the orientation of the polarization. You can see here in the green and the purple that the optical infrared polarization has orientation stays where it is. Whereas the X-rays rotate around by a full more than 360 degrees. Something that's totally unexpected if this is like one coherent magnetic field orientation. So again, it is completely unclear what actually causes that. Something opposite is actually happening in another H.E.S. plus 21/304, another favorite H.E.S. sources, where again we see very high X-ray polarization, the highest X-ray polarization it has been seen in any laser, 30%. So here, well, there's some indication of change of the X-ray polarization between two time points here. The polarization angle doesn't seem to show anything here. Whereas on the other points are optical polarization. So here the optical polarization is low, but the X-ray polarization stays at one angle. The optical polarization swings around and it's again something you would never expect in a scenario where you have one coherent magnetic field responsible for the entire synchrotron component. So this just summarizes the whole trend, where you can see on the right panel for the different sources the degrees of polarization in X-rays, black and optical blue, red, infrared, systematically the trend high polarization for frequencies. And also a trend in the left panel here, that this ratio of X-ray to optical polarization actually increases with increasing X-ray polarization. That brings me to the summary. We can make a point that high energy polarization might actually be a signature of hadronic particle acceleration in blazar agents, which we found so far that does not seem to be the case. So we have strong evidence for those interjunctive blazars having their X-ray emission dominated by electric processes. Then we a bit about this optical spectropolarimetry, where we can disentangle polarized versus non-polarized components and actually see directly measure a black hole mass if we can actually indirectly measure the accretion disk spectrum and disentangle it from the synchrotron emission. We see the systematic trend in high synchrotron peak blazars that the X-ray polarization is systematically higher than optical. We have some evidence for energy stratified emission there with localized emission well optimized magnetic fields, lower energy emission being emitted at larger scales with less ordered magnetic fields.
Thanks, Markus. Some questions or comments?
What is this? Optical conversion.
See any
Polarization angle being because you have shown the spectrum where the polarization degree flux. Is there an angle change?
within the optical typically not? So that seems consistent with Slinger. This angle changes with time. Not frequency.
Yeah, yes.
So, in case of instability, so how the polarization will be affected?
Instabilities, well, will probably disrupt magnetic field structures, so you would probably expect them to where polarization will decrease. And you might have weird features like polarization of the swings as well. Again, that's one thing that H.E.S.S giants actually work quite a lot on polarization signatures from peak instabilities. So if you're interested, I can recommend that you look at some of those papers.
In modeling the ratio or in predicting the ratio of optical X-ray polarization in the single zone approach, I suppose you take the same Lorentz factor, but both these emissions. Whereas in this picture for the shock, the high energy radiation comes closer to the shock, and the optical is then behind. Assume the same but Lorentz factor for the two emissions.
I don't think it would make much of a difference. I see. If I change the polarization angle, it will take because of things, but it would not change the polarization.
Is it an assumption? Because of Lorentz factor doesn't change the separation from the shock.
Sorry?
The bulk Lorentz factor doesn't change with the distance from the shock.
It's very well possible. This is true. We're not that much into this result.
Any other questions? There is a question in the chat window. Maybe you can check in Zoom. Yeah, yes, there.
See? With my IXPE, can we comment on the topology of magnetic fields? Also, comment on the topology of the magnetic fields. Yes, most likely. So this noise support is in areas of helical magnetic fields where the wider component gets compressed by shocks. And then turbulent behind the shock. But it's still very speculative. I don't think we really have good evidence to go into that much detail. We can only have some indication that the magnetic fields are compressed in localized region and they become ordered types. What exactly the topology is, I don't think we can really test this. But turbulence, in those cases, you just expect more turbulent magnetic fields. That's really you expect less ordered particular structures by polarization.
What is necessary that for the equation this polarization law is zero. We have seen this in other agents, or is it that we're seeing a baseline disk which is zero, or
yes, it's right. In the case of Blazars, we see that it's essentially have phase, we don't really expect polarization. So in cases when we see EGN well, we have stable effects that we can use polarization.
so observation we see regular agents having polarization?
Yes, so So super galaxies where we see them or spiritual orientation as actually changes.
Yeah, Markus, see this stratified emission region. So in fact, ions follow the same way, but there's a one confusion always I think is the shock when you compress the field. So basically, the particle diffusion is basically cross field diffusion. So the cross field diffusion is a very inefficient way of creating a stratified region. So that means if it is an aligned field, then the particle, the stratification can be much larger. So since the field is being perpendicular, the way the particle diffuse will be actually cross field diffusion. So even though the observation supports there is significant stratification in the region, but if we really consider the magnetic field to be perpendicular, so then the stratification can be limited. Even I have the same model, I introduced my own model.
I don't think it's flipped to one. You still have a helical field, you just have compressed the two orbital fields. So you still have particles still have a chance to just vary around. Otherwise, you would expect just to maximum polarization between 60-70%, which we don't see.
It's interesting to know that you can easily separate out the this component and reject component the polarities. So because you can separate this reliably the disk component. Is it possible to infer and approach the nature of the disk that is important? Let's say standard disk or some clean or something like that.
Whatever you can say from an indirect inference of the accretion disk, I don't think we can go into that much detail.
I guess like we can look like 2 or 3 points you get in the optical plane, 4 or 5 points, and that's the part. Okay, so if there are no further questions, let's thank the speaker once again. Workshop participants, we will have our regular program 5:30. You know, the snacks will be here for you.
I was thinking that is there any relation between the magnetic field's direction and the EDP of the polarization angle itself?
Sure, it's always perpendicular.
Exactly. Then can it be an effect like as we have a helical magnetic field and the emission region, sometimes we think that they are plasma blobs that are moving. So when they are moving, they are facing the magnetic field in different direction that is rotating. Can that be an effect of this rotating kind of magnetic?
That has been suggested.
The problem is not every time we see the
Guten Tag.
Hello.
Sie sind morgen hier? Morgen auch. Aha. Das ist gut. Wie wir besuchen? Wie wir besuchen?
No, I was just going to introduce.
That's a nice talk.
Yeah, no. Hi, I'm Shalmoli from India. It's right across the road. There's same here. There's I've read most of your papers. Yeah. So the thing is, I work on observational astronomy, radio observation, radio polarization observation of CFOs. So we work on this stuff only, like the magnetic fields in CFOD, radio quiet sources, and we are finding some helical field signatures from the RM gradient. So we actually measure rotation measures, and from there we see a gradient along the transverse direction, and from there we are seeing very weak jets also. We are seeing the signatures of helical fields. But the thing is, again, from the RM gradient, people deduce that it might be an helical field, but there's